In the last chapter or two of this course, we're going to look at a topic called integration. And we're going to start by doing a process called integration by sight. The subject of calculus is divided into two distinct branches. The branches are differential calculus, which of course is what we've been studying for the first 3 or 4 chapters of this course. Differential calculus, as you know, deals with the concept of slope or rate of change. We're now going to turn our attention to the other branch of calculus, which is called integral calculus. Now, the first thing I want to mention is, and I've indicated that by this diagram right here, is that the process of taking a derivative or differentiation is simply the inverse operation of integration. So what we did for the first part of this course is we learned how to take a function f of x, and going through the rules of differentiation, we learned how to move over to a new function called the derivative of the function f of x, which we indicated by the symbol f prime of x. In integration, all we're doing is trying to go backwards. We want to take the derivative and we want to work backwards and find the original function. That process is called integration, or sometimes it's just simply referred to as finding the antiderivative. Now, in this first section, what we're going to do is find the antiderivative or the integral by using a method called trial and error, or some people just refer to it as integration by sight. So we're going to begin our study of integration by doing an example. So what I have here is a function f of x that's unknown to us. The question says, find a function f of x for which the derivative is f prime of x equals 4x cubed plus 6x minus 10. So we don't know the original function f of x, but we do have here its derivative. So the question is can we work backwards and find the original function f of x? So let's think back to our power rule. The power rule of differentiation says that when you take the derivative, you always end up subtracting 1 from the power. So if I just concentrated on this first term, if I just looked at the 4x cubed, and I said to myself, what must the original function have been? A reasonable first guess would be to think that the exponent would be 1 higher. So I'm going to make my first guess 4x to the 4th. Now I can quickly verify whether that's correct or not by taking the derivative. If I take the derivative of f prime using the power rule and the constant times a function rule, the 4 gets multiplied out front and I subtract 1 from the exponent. So if the original function had been 4x to the 4th, then the derivative f prime would have been 16x cubed. But of course, I didn't want 16x cubed, I wanted 4x cubed. 4x cubed is smaller by a factor of 1/4. So what I should have done in my initial guess, instead of having 4x to the 4th, I should have divided by 4. So my initial guess, I'm now going to just tweak it a little bit, and I'm going to make my initial guess x to the 4th. Now when I take the derivative f prime, I get the result that I want. This is called integration by sight, or simply by trial and error. We're just working backwards. So what we do is we go through each term in the original, in the derivative. So we look at 6x. And again, the more of this that you do, the better you'll get at it. But for now, just make an initial guess. The initial guess would be that the power should be higher by 1. So you make your initial guess 6x squared. You take the derivative to verify whether you have the right answer, and you get 12x. You then realize that the 12x is twice as big as the result that you wanted, so therefore your initial guess was twice as large. So my initial guess, f of x, is going to be changed, and I'm going to try 3x squared. And then quickly verifying it, I take the derivative, and I see that it works. So that's the process that I want to show you in this first section, is finding the antiderivative or the integral by trial and error. If you look at the last number is minus 10. So the question is, what would be the original function that would give minus 10 as a derivative? Well, recall that when you have a number like minus 10, which is a constant, you can think of it as being negative 10x to the 0. So if I add 1 to the exponent, I would have had x to the 1. So I'm thinking that my initial guess should have been minus 10x. And of course, taking the derivative, I see that that holds true. But there is one little catch to this. How do we know that the original function didn't have a constant? Because if you recall the constant rule that we learned earlier in the course, If you have a function f of x that's equal to just some constant c, then the derivative f prime is going to be 0. So if you look at the original derivative that I gave you, there could have been something behind this minus 10. There could have been just a number 0 that disappeared when we took the derivative. This is one of the problems with finding antiderivatives or integrals, is that we can't really find the original function without some other information, because the original function, for all we know, could have had a constant. So when you find an antiderivative, what you have to do is indicate that there's always going to be some constant, and usually we use the letter c. So for this particular question, we would say that if the original function had a derivative f prime of 4x cubed plus 6x minus 10, then the antiderivative would be some function, and I'm going to use capital F of x to indicate that. The original function capital F of x, or the antiderivative, if you look at what we determined here, it would have been x to the fourth plus 3x squared minus 10x, and then we have to indicate that there might have been some constant c. That constant is unknown to us at this point, but later on we'll see that we can actually determine that value given some initial conditions on the question. So this letter c simply refers to any constant. Based on our last example, we can now write down the very first rule of integration called the power rule. The power rule of integration is just the inverse rule for the power rule of differentiation. And if you recall with differentiation, when you had a power x to the n, you always multiplied the power out front and then subtracted 1. Well, integration is the reverse process. So we just do everything in the reverse order, backwards and reverse. So instead of multiplying and then subtracting, we add and then divide. So if you have a function in which you know the derivative f prime of x is equal to some power x to the n, then to find the original function f of x, simply add 1 to the exponent, so x to the n plus 1, and then divide by that value, 1 over n plus 1. And don't forget that we always have to put our constant c, some arbitrary constant that we aren't aware of at this point. Now we're not just limited to powers and polynomials. We have also learned in this class how to take derivatives of other types of functions such as transcendental. So another example we could do would be, suppose that the derivative of some function f prime of x is equal to the sine of 4x, and our goal was to find the original function f of x. Well, if you recall when you take the derivative of sine and cos, that the derivatives are just the opposite function. So the derivative of sine is cos, and the derivative of cos is negative sine. So if I was going to make a guess here, my initial guess for f of x, I know that since the derivative is sine, that the antiderivative should be cos. So I'm going to make my first guess for the function f of x to be cos 4x. It's a logical choice. Now if I take the derivative f prime, the derivative of cos, if you recall, is negative sine. The part that's inside the function, the 4x, is called the argument, and it doesn't change. So the derivative would be negative sine 4x. But then if you recall, we always have to multiply by the derivative of the argument, which would be times 4. Well, that leads to an answer then of minus 4 sine 4x. So what we do is we look at that, and we ask ourselves, how is that similar and how is it different from what we're looking for? We're looking for a derivative of sine 4x. Well, I have the sine 4x, but I also have a negative and 4 in front, which I don't want. So what I'd have to do is I'd have to divide this by negative 4 to get the result I want. So therefore, I'm going to alter my first guess, and I'm going to suggest that my first guess, f of x, would have to be negative 1/4 times the cos of 4x. Don't forget, we always have to put an arbitrary constant c. Now the nice thing about integration is you can always verify your answer by just taking the derivative. So if that is the correct answer, then if I differentiate this function, I should end up with what I started with. So it's always a good idea to take the derivative to just confirm that you have the right answer. So I've got negative 1/4 as a constant. I take the derivative of cos, which is negative sine 4x, and then I multiply by the derivative of the argument. The derivative of c, of course, is 0. I see that the 4's cancel and that the negatives multiply together to give me positive, and I get the result that I wanted. So my final answer, the original function f of x, given this derivative, would be negative 1/4 cos 4x plus c. So again, this process is called integration by sight, where we're just basically making a guess and then altering the guess until we get the result that we want. Now at this point I want to introduce you to the notation. When we take derivatives, we have special symbols for it, like f prime or dy dx. Well, we also have symbols to indicate that we want to take an integral. So the symbol for that is a strange looking thing. That symbol right there is called an integral sign. Now there's a reason for its shape, and we'll probably get into talking about that later. It's actually the letter S that's sort of been elongated or stretched out. And there's a reason why that was chosen. But that sign simply means that you want to find the antiderivative. So instead of always writing out the question with words saying, please find the antiderivative of the following function or the integral, what we can do is simply indicate that with the sign. So if I give you something like the integral, and that's how you would read that, you would just say, find the integral, and then inside the integral sign, you would have your function. So for example, find the integral of the function x squared. Now there's something else that has to go in here, and I'd like to talk about that a little bit. You may recall when we take derivatives, it's essential that when you take a derivative, that you indicate with respect to what variable. Like if you had a function y equals x squared, and you want to take the derivative, you'd have to say that you want to take the derivative with respect to x, which would be 2x. Otherwise, you might be taking the derivative with respect to time, for example, as we saw with the chain rule and related rate problems. So when you're taking an antiderivative or an integral, you also have to indicate the variable you're taking the integral with respect to. So what goes behind the x squared is the symbol dx. So you would just read that. What is the integral, which just means what is the antiderivative of the function x squared with respect to the variable x? The part you're taking the antiderivative of is called the integrand. And this dx simply indicates the variable that you are integrating with respect to. So don't let that bother you. That doesn't change how you do the question. It simply has to be there to indicate that you're taking the integral with respect to x. Now overall, this whole expression is given a name. It's referred to as an indefinite integral. And the reason why it's indefinite is because we don't know the value of c. We're going to see later on that we're going to look at what are called definite integrals, where it becomes a bit more precise. So if I was actually doing this question, the question is saying, what is the antiderivative or the integral of x squared with respect to x? I would just say that the integral of x squared with respect to x is equal to, now because this is a power, I would just use my power rule, which says to add 1 to the exponent and then divide by that number. So that I know that the answer is going to be x cubed, but then I'm going to multiply by 1/3 to compensate for the 3. And don't forget to always put the arbitrary constant. So this symbol says, take the antiderivative or the integral of the function x squared with respect to x. And this would just be the answer, 1/3 x cubed plus c. I want to turn our attention now to a very interesting situation. We've seen that using the integral rule for powers, that we basically can find the antiderivative or the integral of anything that's raised to a power. So for example, if I wanted to find the integral of x to the 4th dx, I simply would add 1 to the exponent, so x to the 5, compensate by putting 1/5 in front, and then going plus c. Now, obviously, that's going to seem to apply to any power. I mean, it doesn't matter whether it's the integral of x to the 3 dx. You're still going to go 1/4 x to the 4th plus c. The question is that ever going to get us into trouble? Can you think of a situation where you would have a power where the power rule of integration would let us down? Well, let's turn our attention to a function that looks like this. What if we wanted to find the antiderivative, or the integral, of 1 over x dx? Now, 1 over x is a reciprocal function, which can be written as the integral of x to the minus 1 dx. But look what happens when we try applying our power rule of integration. The power rule says that to find the answer, we are to add 1 to the exponent. So if we add 1 to negative 1, we get 0. And then we're to multiply by 1 over that number. So of course, we end up with something like this. 1 over 0 times x to the 0. Well, 1 over 0 is undefined. There is no such number. And so we seem to have a problem. We seem to have one power, the power x to the negative 1, that doesn't have an antiderivative. Now, if you think back to the previous chapter when we looked at transcendental functions, you may recognize that 1 over x. That 1 over x, if you recall, was the derivative of the natural log function. If you had the function y equals the natural log of x, then the derivative, dy dx, was 1 over x. So since integration is the reverse process of differentiation, it stands to reason that if you wanted to find the antiderivative of 1 over x dx, that the answer would be the natural log function. I find that to be a very interesting fact, that the only function that we can't use the power rule for, the function x to the negative 1, it seems like we're at a bit of a standstill, and the natural log function, if you might say, comes to the rescue. If it wasn't for the natural log function, we wouldn't be able to take the antiderivative of the function 1 over x. So this leads us to a rule then that says if you have a function y equals the natural log, and if you recall from previous studies that it can be the absolute value of x, then the derivative dy dx is 1 over x. So our rule of integration will be that the integral of 1 over x dx is going to be the natural log of the absolute value of x plus c. And for one final example, sometimes, since we're working by the process of trial and error by sight, we can potentially get questions that look kind of complicated. Suppose you wanted to find the integral, or the antiderivative, of x to the 4th times 2x minus 3 dx. Now, as soon as you get into products and quotients, if you recall from our rules of differentiation, things get a bit more complicated. So if you want to find the antiderivative of a product, it's not simply a matter of doing the by sight method. So what we have to do in this section, until we learn some other techniques, is we basically just have to write the question as a polynomial. So what I want to suggest to you with this last example is sometimes it's necessary to simplify a function before you take its antiderivative. So what I would do here is I would simply multiply the x to the 4th through the brackets. So I would have 2x to the 5th minus 3x to the 4th, all with respect to x. A function that's written in this form as a product is very hard to find the antiderivative of. But in this case, we're able to actually multiply and get rid of the product, and now we just have a polynomial. So as you're working through the assignment, as you get later into the assignment, some of the questions will require you to use some simplification skills before you actually try to find the antiderivative. So in this example then, the actual answer, we would just add 1 to the exponent, so x to the 6th divide by 6, which would give us 1/3, subtract, add 1 to the exponent, divide by 5, and don't forget to put your constant of integration, the value c. Okay, so that ends our first section of integration by sight. In the next section, we're actually going to use a different technique to find the integral of a function.